next speaker for this session is Professor Venkatesh Kodur, who is a University Distinguished Professor in Civil and Environmental Engineering at Michigan State University. Now, of course, many of us in India have had the advantage of listening to Professor Kodur. He is one of the leading experts in fire and its effects on concrete structures. He has over 350 peer-reviewed papers with numerous citations. And apart from being chairman of the ACI Fire Protection Committee, he was also part of the assessment team that studied the collapse of the World Trade Center buildings on September 11. Without further ado, let me invite Professor Venkatesh Kodur to share his talk. Professor Kodur?
Yes, can you hear me?
Yes, very much. Yeah, sure.
Okay, so let me go and share my screen. Can you see the screen now?
Yes, that's correct. We can see it. You can just put it on slideshow mode. Yeah, fine. That's perfect. Thank you.
Perfect. Good. Okay. So, just one. Okay. I don't want to say good morning, good afternoon. We are all in different time zones. And I am in Michigan, United States, where it's just past midnight right now. It's 12:30 a.m. So, first of all, I would like to thank Professor Gettu, as well as Rilem and Gettu's colleagues, Manu Santanam and others, for organizing this workshop, as well as for inviting me to be part of it. So the title, Manu, can you hear me?
Yeah, I can hear you. It's clear.
Sure. So, the title of my top presentation is on strategies for enhancing resiliency of modern concrete structures under fire hazard. The buzzwords here are resiliency, obviously, modern concrete structures, and fire hazard. So those three are the buzzwords here. So what I'm going to do today is to just give you some background information to the overall importance of fire safety, specifically mostly in buildings, but in infrastructure, critical infrastructure. Then I'm going to also look at the resiliency, why resiliency is much more important in the current or the modern concrete structures as opposed to structures, 30 years ago. I'm going to look into that. And I will illustrate, in addition to that, some of the fire statistics, we call it, to see how the magnitude of the fire problem itself around the world. After that, I will move on to a brief mention of various experimental and numerical studies we have carried out to develop techniques and technologies to overcome the fire problems with respect to especially the new concretes. I'm going to discuss some of the critical parameters, and finally at the end, I'm going to quickly point out some of the innovative strategies that can be implemented even in new concretes and new structures to overcome not only the fire problem, but also how we can enhance resiliency. Okay. So as we all know, concrete is the most widely used construction material in most countries, or if not in all countries around the world. And there are a number of advantages. A lot of times, all these advantages students are taught very well, even in their early concrete courses. But one of them, which is conveniently forgotten, is it was started because with timber or steel has a lot of significant problems with fire resistance. I will define what fire resistance is. So one of the best materials from fire safety point of view is concrete for structural members. That's why it's widely used as well. There has been significant research and development activity with respect to concrete, especially from the material point of view. And this has led to a lot of new concretes, such as high-performance concretes, they call it, or high-strength concretes, ultra-high-performance concrete, fiber-reinforced concrete. And much of these concretes are provides very good strength, stiffness, durability, sustainability, you name it, much of the needed properties. However, with the recent concretes, one of the problems is fire, which we will come to that in a second. Before that, fire is a major hazard in the built infrastructure, and especially in buildings because of the life safety requirements. Fire poses a significant hazard and threat to the built environment. And conventional concretes usually used to have much higher mass and much higher fire resistance, but same is not true with the new types of concrete, which I'll show you quickly. Now, the emerging trend over the last 30, 40 years, in most parts of the world, is to resiliency is the key buzzword for critical infrastructure. Okay, so this includes buildings, bridges, tunnels, whichever we classify them as critical especially. So concrete structures exhibit very high levels of resiliency in terms of safety, robustness, disaster resiliency of the different materials. However, today in the current way of doing things, we evaluate this resiliency or check for this resiliency in critical infrastructure, especially under blast, earthquake, impact, but we don't do it even the basic things for under fire hazard. It's all based on the prescriptive approaches developed 40, 50 years ago, which are present in the codes and standards. It's not in any country, even in the US, for example. These are all tests based on single test done on columns at underwriter laboratories or NRC Canada. Still, we continue to use those provisions which are not really applicable for the modern construction. So fire resistance and basically, since we don't evaluate this resiliency specifically under fire hazard, modern concrete structures are susceptible to problems, especially under fire. Now, I don't want to spend too much time. Fire, as you all know, is a significant hazard in terms of statistics, as I mentioned to you, not only for people, but also for infrastructure or structures. This is some of the statistics. In the US, there were more than 1.3 million fires and led to more than $50 billion of damage in 2017, almost about 2% of our GDP. Now, when fire happens, remember it can start if something goes out of control. Either lightning can start a fire on a bridge, for example, or something going out of control in kitchen can start an accidental fire, electric short circuit. That's primary event. Also, fire can start following a blast happening somewhere or an impact. A truck hits a bridge, that impact doesn't do much damage. The bridge is designed for that, but it's not designed for the fire which follows that. 9/11, the 9/11 buildings were designed to account for the impact loading of a smaller aircraft, not that aircraft. I was part of that investigation, but when we looked at it, it was never designed to account for the fires that ensued the impact loading. So similarly, even floods can lead into fires, as it happened in New Jersey in 2012 Hurricane Sandy. So as a secondary event, fire can do much more damage than the primary event itself. Now, it's impossible to prevent all the fires, okay? And so proper measures are to be put in place, such as sprinklers, heat detectors. You put in a lot of things, heat detectors, smoke detectors, exit pods. These are all called active systems. But one additional thing we need is the structure has to stand up till that fire can be fought or fire can be extinguished. And this requires your structure to stand up. For example, in 9/11 buildings, right? The buildings, for example, collapsed not because of the plane sitting. It would have been standing today. That's the conclusion of the official report. It collapsed basically because of the huge fires which ensued after the impact loading. Now, in order to do this, and it's very important from life safety, property protection, and everything. So if you have higher fire resistance, you can have higher resiliency in the structure itself. Now, there are a number of fires around the world. Now, these are some of the recent fires in the United States. For example, the damages which happened in November 2018 California wildfires is more than $3 billion. These for structures. and more than $26 billion of insurance was paid out because of that. This was not major structures because it was in the outside the towns, but there was some kind of damage to some structures as well. Now, in addition to that, 9/11, obviously, you all know much more about this. There was bridge fires in the United States, tunnel fires, for example, warehouse fires. So fires do happen. Oakland warehouse, where 36 people died again in Oakland, California. So and in this case also, there was significant structural damage. Now, I'll just illustrate you, there is not much time in today's presentation, but quickly illustrate you how things can go wrong. This is an I85 bridge outside of Atlanta, Georgia, Atlanta airport. And on a fine day, on a fine evening on 30th of a spring day, or spring has started, on 2017, what happened was they put in underneath the bridge for repair, drainage repair, lot of pipes, polyvinyl PVC pipes, polyvinyl chloride pipes. And then they left it and went because they wanted to start the work late April or May. All these pipes were here. A homeless person, it was a cold evening, so he comes in and sets fires to all the rubble or paper which was around it. And then that goes out of control and goes into the pipes, and huge fire starts. And look at this fire, which was fire department because it was closer to the city, Atlanta. So a lot of fire engines came, or firefighting trucks came, couldn't be fought. They had to withdraw because of significant spalling. You can see this here, rebars completely exposed, spans of the bridge collapses. You won't believe how much damage. Delta had to cancel about 1,000 flights over the next 3 days or more because nobody could get to work all the flight. That's the hub of Delta, where it's world's largest airport, basically. So I think that's the kind of damage that can happen, and it took weeks for the bridge to be rebuilt. There are a number of buildings. I can name, hundreds of buildings which were on fire in the last 5 years. Important buildings is Tehran, Pasco building, 17-story building collapses. Number of firefighters died as well as people died. Grenfell Tower, you know that what happened in Grenfell, concrete building. The first one was a steel building. I was part of the investigation at Delft University of Architecture, university building, 13-story building which collapsed because fire started due to an electric short circuit in a coffee kettle, okay, which was not turned out, and it starts. So there are a number of fires in the building, so it's a real hazard which we are looking at. If you look at the world statistics, as you can see this here, India especially, for example, has the worst fire record. Nearly 24,000 people die every year because of the fire incidents. May not be due to structural damage, but fire as a whole thing has to be considered as an hazard. A lot of times smoke is the one which kills more people than anything to do with the structure itself. Now, how does the current codes address this? Current codes address this by putting a lot of fire protection measures, and this depends on the height of the building, what type of occupancy. For example, if you have buildings which have old age people or hospitals, then obviously you need to provide higher fire resistance, or it should stay longer than an office building, for example. So these are put in place in the building codes, including in India, and every other country has this. So without that, you cannot get permit to have the building. And what is the fire safety strategies? We put in a lot of measures, as I said, sprinklers. Fire comes out, it should be put out by sprinklers automatically. Most buildings in the United States, new buildings are sprinklered, but often sprinklers are not effective. So then people has to be sent out. Then you have fire to be contained to the source of the origin in one compartment or one room or two rooms. That's done through barriers, or your structure has to stand up till the fire is fought. This is what is called as the fire resistance. And depending on the height, depending on the occupancy type, you need 1 hour, 2 hours, 3 hours, or 4 hours. Under so-called standard fire, the building has to stand up. Okay? So I will skip this slide. So fire grows something like this. Just remember this. Nothing happens to the structure here. I'm talking more about structure. People should get out at this time. But for structure, this is the part where structural fire resistance comes into play. So typically you need 2 to 3 hours of resistance in structure not to collapse under fire. Okay, so this fire resistance depends on a number of factors, and including what kind of a fire you have, what's the type of materials you have, whether it's a concrete, steel. You can see that this is loss of strength with temperature. Different materials lose strength at different temperatures. So all this has to be accounted for. Now, current provisions, if you take conventional concretes, is really very prescriptive. As I said, much of this is developed based on 60s and 70 concrete types and technologies. And as you can see, all you need to do is power certain cover thickness to the rebars, because steel is a weaker part in this slab, or in this one as well. As long as you have sufficient cover thickness to the rebar, you have achieved certain fire rating. More fire rating or more fire resistance you typically get with a higher cover thickness. Now, American codes are so prescriptive, there is no other way of engineering the system right now. For 1 hour, as long as your dimensions is 8 inches minimum, that's 200 millimeters, you get 1 hour in a column cross section, and you need to provide 1 inch concrete cover for getting 1 hour rating. For 1.5 inch, if you provide concrete cover, then as long as your minimum dimension is 9 inches, then you are going to get 1.5 hours rating, and so on. As simple as that, which is not realistic. Now, what about Euro codes? Very much similar. Look at this. In one table, they cover beams, columns, slabs, and walls, and same approach as this, very prescriptive. Now, I have to move on quickly because of the time. So modern structures are significant problems because they are typically taller as opposed to 70s, 40s, 50s structures, and they are leaner. I will show you that, and they are made of new types of materials. Newer the materials, lower is the fire performance, and we have increased demand on the modern structures because we use all this nonlinear analysis and all this and make the structure very slim. Okay, so the current codes, typically, if you take the modern structure, they have lower fire resistance compared to the equivalent structure of yesteryears. Now look at this modern slabs, how different they are. If you take solid slab, hollow core slab. If you take a column, look at this, how small we are building with higher strength concrete. Same thing, we are using this type of shapes. Similarly, our concretes have much more problems because we increase the concrete strengths and it comes with lower permeability. It's susceptible to two things. One is because the strength of the newer concrete, see this red line, this is how the strength drops with temperature. Look at the normal strength conventional concrete, slowly drops. So this is the major problem. The second bigger problem is the occurrence of so-called fire-induced fall. Look at a concrete column, 6 hours in a fire, which I tested, nothing happened, 16-inch column. This is typical column used in Chicago. And look at the column, high-strength concrete column in 19 minutes. This was done for Portland Cement Association and Construction Technology Laboratories. I did these tests at NRC, about 15 columns were tested for them in addition to a number of other things. So we developed a lot of guidelines. So this falling, basically why it happens is buildup of when it's exposed to fire, this has lower permeability, moisture becomes vapor, it can easily get out here, 10 to the power of minus 16 is the permeability. When you reduce it by 100 to 1000 times to 10 to the power of 18, that pore pressure converts into the tensile strength and pushes this out. So boom, 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 throughout this fire scenario, you will have spalling. And this spalling can reduce fire resistance significantly. We did number of tests, and we did the material property test. Over 30 years of my research is focused on this, first at NRC Canada and then at Michigan State University now. And we developed about 15 PhDs so far have graduated on this related topics. So we have developed advanced analysis models, and recent work has been to develop much more guidelines as well as with ultra-high performance concrete. See, the concrete, as I said before, current codes say only cover thickness is the issue, the size of the member, but it is affected by so many factors. Strength of concrete, reinforcement layout, density of concrete, type of aggregate, whether you're using limestone or quartz. So there's a number of things. As you can see, higher strength concretes, conventional concretes, but if you add fibers, you can significantly minimize this falling which is happening. Okay, so another thing is if you bend the ties, it enhances fire resistance significantly. Okay, so bending the ties at 135 degrees, this we did for PCA and this is in American courts right now. You can reduce falling significantly even with higher strength concretes. Then concrete, when it is subjected to a column, for example, when it is subjected to concentric loading, under fire, you have episodal falling happening in different sides. So that means your concentrically loaded column becomes eccentrically loaded, either due to development of thermal gradients when only one side, two sides, or three sides exposed to fire. So a three side exposed to fire, two adjacent sides exposed to fire can be much lower fire resistance than a four side which is exposed to fire. This can cause significant problems in real life. Okay, so let me skip this. How can you overcome this? If you can add polypropylene fibers, these fibers are 0.1 to 0.2% by mass, by volume. So they melt at early temperatures of 160 degrees and increases the permeability or create pores where the pore pressure can easily be dissipated. If you add steel fibers, it increases the tensile strength and it significantly overcomes the pore pressure. It withstands the pore pressure so that there is very less falling. Okay, you can do few other things. So look at the columns we tested. These are all tested in the lab. Plain concrete, polypropylene fibers, no spalling, steel fibers, very little spalling, as well as hybrid fibers. You can change the configuration. If you provide the ties like this, it does wonders. It increases the fire resistance. Instead of failing this column in fire 1.5 hours, it can go up to 4 hours by just bending these ties or by providing cross ties. Okay, and there are very minor other things like changing the aggregate and stuff. I'm not going to get into this. The last point I want to make is that you have to engineer it and you have to use advanced analysis approaches wherein at a system level, you need to account the realistic fire which can happen in a structure, realistic material properties, if it is high strength concrete, high performance concrete, ultra high performance concrete, whatever it is. Then you have to account for this falling and other things which are very complicated even at this stage. These are all PhD topics, for example. There is very little data. And then you can carry out the analysis, first finding out the fire scenario. Then you find out the temperatures. And then you calculate the structural response. And then include all your spalling, creep, bond, degradation. Everything changes with temperature. That's where the complexity gets in. Okay. So we have done a lot of this. It's published in number of journal papers. But let me conclude here. So resiliency of structures should be one of the critical conditions or critical considerations under fire hazard, especially with modern concretes construction. There are very few problems with respect to conventional concretes, but same cannot be said about the modern concretes. High-strength concrete structural members are ultra-high performance concretes. They exhibit lower performance as compared to conventional concretes, as well as significant spalling problems. So you have to have engineered the system through advanced analysis. We call it performance-based design, but you have to use advanced calculation models so that you can develop unique strategies for overcoming this. Okay, so as I showed you, simple modifications such as straight configuration of fibers can help in overcoming this problem. So this is one of the recent articles in ACI, very general article in Concrete International. So there are a number of journal papers associated with this. And finally, I want to say this: there are very limited books in the fire engineering area. This is one of our recent books. It addresses not only concrete structures, steel, wood, timber, masonry, FRP, all structures, how to design for fire. This is a new textbook which just came out from McGrail last month. And thank you all for your attention.
Well, thank you very much, Professor Kodur. Indeed, that captured many different aspects about concrete structures, resistance to fire. Of course, as you said, the time was limited to really discuss everything in detail, but I think what you presented gave across a clear sense of an understanding of what needs to be done to improve resiliency in buildings with respect to fire. We have a few questions.
Okay.
Of course, as expected, one major question is about the World Trade Center collapse in terms of what was the phenomenon that ultimately led to the collapse. So your thoughts on that in just a few words. Yeah.
Sure. So basically, I think if you, in simple terms, all this was due to fire. When fire happens, especially the major defense for firefighting could not happen. Sprinklers did not work in the World Trade Center because it was not meant to be for that kind of fires. The third defense we have, so sprinklers gone, firefighting didn't happen. The third defense was structural fire safety. They were all steel structures. In steel, they collapsed in 20 minutes, a steel column. But we had insulation around it. That insulation, because of the impact loading from the plane, the insulation came out, fire insulation. So steel was directly exposed to fire. Huge buckling in the columns. The intermediate force, buckling length of the columns increased significantly because the intermediate truss systems failed, which were connecting the columns. So huge buckling led to progressive collapse, one after another. No way it could be stopped.
Thank you. Another question is, can elevated temperature lead to the densification of concrete at the microscopic level due to melting of some components?
Yes, it's possible, especially when the temperatures go beyond 500, 600, 700 in the microstructure, yes.
The other question is, can geometry of the structural elements help reduce vulnerability to fire damage? Can we design for structural elements with a different geometry and increase the fire resistance?
Yeah, it may be possible, but architects don't like it. For example, circular columns are typically better than the square columns. But in buildings, even that I can say, because circular columns are used in bridges, we have done a lot of work on that as well. So that has much higher fire resistance than square columns or a rectangle because of the corners. But architects don't like that. So fire is a secondary event, you have to satisfy that. So that's one of the major issues as well. Yeah, but with some cross sections, it can give you higher fire.
Are there specific mix design and mix selection procedures or methods by which we can increase fire resistance of the concrete? Can we select materials appropriately? Sure. You of course talked about fibers.
Yeah. Then limestone instead of granite will give you higher fire resistance. That's the easiest thing I can tell you, about 10 to 15% easily higher wherever is available instead of granite, as well as less pozzolans or less silica fume and stuff, less those fines is added. You know, concretes, for example, years we never used to have these admixtures, silica fume. The lesser it is, better it is from the fire resistance point of view. But that may not be sustainable, that may not be economical. So that's why more research, more this thing is needed.
Sure. You've also probably had some experience with using pozzolanic additives in cement. Of course, silica fume for high performance concrete, it produces some problems, as you rightly said. Yeah. But in terms of normal concrete, if you use fly ash or slag, does it help in improving resistance?
You know, there is very limited data with respect to fly ash. And unfortunately, I think it shows both sides. Some data shows our data was weaker in terms of fire resistance, but when I look at some other data, it's better. So, but from spalling point of view, it also promotes spalling. It blocks the pores, I think, to some extent, and you know, the permeability aspect.
The other question is, what is the difference between fire design requirement of restrained and unrestrained members? Is there some difference?
That's a $1 million question, not answered in the last 100 years, or still it's confusing. There is no guidelines, no codes, but restraint can significantly influence the level of the fire resistance. During fire, what happens in simple terms, if you have a beam, that becomes, everything becomes a restraint because of the expansion. It's trying to expand, it cannot expand. So these are huge forces. So if you design a beam for a moment capacity, which is, let's say, M, the axial load which produces, you know, axial force which develops, the thrust force which develops can be 50% of the capacity of the beam. So we are not today in most codes and standards, unless you do nonlinear design or advanced design, codes and standards they have some simplified ways of accounting for this, but it's not realistic. In fact, restraint is a major issue that should be addressed in buildings or structures.
One question that is raised is, can we actually have some sort of a modification done to an existing structure to improve fire resistance?
It's for steel structures, obviously putting insulation is the easy thing. That's the thing which we follow always. For concrete structures, this is one area I think where much of the material scientists I think can do a lot more, is to come out with some kind of coatings and stuff for concrete. There are not much easily available commercially viable coatings. For steel there is intermittent and so many things, not for concrete structures. So still it's a problem. You need to put insulation, but that's not effective for concrete structures.
Sure. Of course, there's several questions. I'll probably pick a couple of them for you, because I know that you answered a lot already, and I'm sure that we'll also have to move on to the next talk. Now, are there specific indicators that we can test in the concrete to evaluate its resistance against fire? For example, we have several durability indicators. Can we have some specific properties that we can test so that we can qualify the concrete as being good against fire?
Yes. So typically people around the world do this so-called compressive strength and tensile. The tensile strength was never tested. Till about 10 years ago, nobody even looked at tensile strength of concrete with temperature. See, properties change with temperature. And this tensile strength was not important, because at room temperature, it's 4 megapascals. And at elevated temperature, it drops to 1. Even at room temperature is not important. But today, because of this pore pressure, the tensile strength at elevated temperature is the one which resists, that's falling. So it's very important for new concretes. And I keep talking to Ravindra as well. The Rilem has some standards, except Rilem ASTM doesn't have standards. If people do in different ways, there are very lack of standardized methods and tests for this, obviously. The indicators are compressive strength, tensile strength, and, yeah.
And finally, just one additional question. What type of structural system would be ideal in resisting a fire load? Would it be a truss or a tension member, compression member, or something which experiences composite action?
Yeah. So I think ideally, if it is a beam, or it's very good, especially if you can design or if you can account for those restraint forces. That will be helpful to resist much more. It depends. Restraint is very good for fire resistance. A beam which fails in 1 hour, if you account for the restraint and design properly, it can last for 2 hours easily. So it helps because that restraint force keeps changing from compression to tension throughout the fire and stuff. But where the location of that restraint force has to be properly accounted for in design or in connections.
Thank you, Professor Kodur, for patiently answering so many questions. I know there are a lot more on the chat window. If you do have time, and if you're not feeling too sleepy, if you can address a few of those directly through the chat itself. I'm sorry that it extended so much into your night, but I'm sure it's been really enlightening for the audience that has had the chance to listen to you today. So again, thank you very much.